linearization of the predator-prey system, also known as the Lotka Volterra system. So it is described by this state equation here, and we have to linearize them around a non-zero equilibrium point. So the state equation is the following. For the prey, the population of prey, it is an evolution which is exponential, and the coefficient in front of exponential increasing is related to the predator as follows. So x2 is the population of predators. So we can understand that when there is no predator, the population of prey increase exponentially. And it is also for the derivative of the population of predator, it is something which is exponential but a decreasing exponential. So -1 here if there is no prey, but when there is prey, the number of predators tend to reduce the effect of this decreasing rate, and if x1 is greater than 1, we can see that it becomes an increasing exponential. So what we have to do first is to linearize it, this system, and around an equilibrium point. So to find an equilibrium point, I have to solve that this function f of x should be equal to 0. So for this we have two cases. The case where, let's say, x1 equals 0. So if x1 equals 0, what happens is that if I want this to be equal to 0, it means that the first line will be equal to 0 and the second line should be equal to 0. But since x1 is equal to 0, then this term is not equal to 0. So it's mandatory to have x2 equals 0. So in this case, I have x2 equals 0. So it is the first equilibrium point corresponding to x equals 0, 0. Now assume that x1 is different of 0. Since f of x equals 0, so it means that this equal to 0 and this equal to 0, this term is not equal to 0, so it means that this one is equal to 0. So it means that x2 equals 0. X2 equal 1. So x2 equal 1. Since x2 equal 1, this term is not equal to 0, so this one should be equal to 0. So it means also that x1 should be equal to 1. So the second equilibrium point is 1, 1. And in the exercise, it is required that we have to linearize around a non-zero equilibrium point. So it is this one. Now, to linearize it, I will approximate by a first order Taylor formula, which tells us that around x bar, so x bar is this one, around x bar, f of x is approximately equal to f of x bar plus the derivative of f with respect to x, so the Jacobian matrix, evaluated at point x bar, multiplied by x minus x bar. So let us recall that this formula is related to this picture, where here I have R2 to R2, which corresponds to f. F is something which is nonlinear, which can be like this, for instance. Whoop. And x bar is here, and here it is the approximation. So the slope here corresponds to the Jacobian matrix evaluated at point x bar. So this is some kind of derivative. And if I take x here, which is near x bar, So we can understand that the tangent is very similar to the function f. So the function f is this one. So in this case, this corresponds to x minus x bar. And here it corresponds to the image that we can call y bar, where y bar is equal to this term, f of x bar. So we can understand that f of x is approximately equal to this term, which is affine with respect to x, and which is the equation of the green tangent plane. Okay, so now since this corresponds to 0, because f of x bar equal to 0, and I have to compute the Jacobian matrix, and the Jacobian matrix I will have to differentiate. So I will compute, since this corresponds to f, this corresponds to f, the derivative of f with respect to x is equal to, so to derivative, partial derivative of x1. So f1 is the first component. f1 x2, f2 the second component, the partial derivative with respect to x1, f2 with respect to x2. Then after I will evaluate it. So if I take at the point x bar, it will be equal to, so the derivative of f1 with respect to x1, we can understand that it is 1 minus x2. Evaluated at x bar, it will be 1 minus x2 bar. The same here. If I compute the derivative of f1 with respect to x2, then I will have minus x1 bar. Here I will have x2 bar, derivative of this one with respect to x1, and minus 1 plus x1 bar, so derivative of this one with respect to x2. Now this is equal, since x bar is equal to 1, it will be equal to this one to 0, this one to minus 1, and this one to 1, and this one to 0. So if I come back to my formula, my Taylor approximation, I get that f of x bar approximately equal to the matrix 0, minus 1, 1, 0, multiplied by x minus x bar, or if you prefer, I can write directly x1 minus 1, x2 minus 1, which is also equal to minus x2 plus 1, x1 minus 1. So it means that this is affine, so it's approximately equal to this. This is affine, and if I define the variation x tilde equal to x minus x bar, the variation is this, which is also equivalent to say that x tilde 1 equal x1 minus x bar 1, and x tilde 2 equal x2 minus x2 bar. Then in this case, I will obtain the linearized system, which is not affine like this one. This one is affine, but the linearized system is the derivative of x tilde with respect to t is equal to 0 minus 1, 1, 0, x tilde. So it's the same as if I approximate here by the tangent, but I also change a frame, and the frame which was red is now replaced by this one, which is magenta, and here x corresponds to x will correspond to x tilde. All the computation that I have done by hand is usually, for engineers mainly, done using symbolic calculus. So we'll do this for this simple example. And for this, we'll use Python, and the symbolic toolbox of Python, the main classic one, is SymPy. SymPy. Okay, so I will import everything. I will define the symbol x1, x2, which corresponds to the variable I will use in my computation. It means that all variables that I will use in the future depend on x1 and x2. So it is all my symbols. So here, what I put here is when I will print the variable, it will print x1 because it's associated to this variable. Now recall that the evolution function f of x1, x2 for my system is equal to 1 minus x2, x1 and minus 1 plus x1 multiplied by x2. So I define f, the expression for f. So it is defined here. Then I will also define the vector capital X, which corresponds to x1, x2. So this one is a function, but here it will more an expression. This expression will be called f. So the Jacobian j, which is here, corresponds to the derivative of f with respect to x. This is why I call the Jacobian like this, the function dot Jacobian, which calls the method Jacobian with respect to x, and then I will print it. So this corresponds to a carriage return \n, which comes from a C syntax, so G equal. Now I want to differentiate near to x1 bar, x2 bar, which are both equal to 1, as we have seen previously. So x bar will correspond to the vector x bar will correspond to x bar 1, x bar 2. So y bar correspond, so I take f here, and I will substitute x1 by x1 bar. Sorry, here it should be x1 bar. They are equal, so we will not see the difference. x1, and here x2 by x2 bar. So this is I substitute. But since x1 bar, x2 bar correspond to an equilibrium point, this one will be equal to 0, and I will be able to check it. So it's still an expression, but some variable have been substituted. Since all variables have been substituted, then of course y bar will be still an expression, but it will correspond to a real number, or here a vector with two real numbers inside. The same for g bar. I will perform a substitution such as this one, and here I will, this is a linearized version. So it is a function which is defined by the Taylor method of order 1, and this corresponds to the tangent y bar plus g bar multiplied by x minus x bar. So it can be seen as a function. I switch to Python. This is my program, and I will correct here. I run the program, and I can see here the matrix J before substitution. Then I have x bar, which corresponds to 1, 1. G bar after substitution corresponds to the matrix I have already computed. Question number 2. Among the two vector fields of the figure here, I have to decide which one corresponds to the field of the Lotka Volterra system, this one, and which one corresponds to the tangent system. So they look similar, normal, because one is the approximation of the others. So I propose first to draw the two vector field in Python, and I will use a symbolic computation for this. So I define as previously my function f of x. I compute the Jacobian as previously done, and here it corresponds to the linearization of the function. Then I will lambdify it. So to lambdify means to transform an expression that I can print but I cannot call into a function that I can call but I cannot print. Okay, so from this fl lambdified, I can call it. And this will allow me to draw a field. So I will use the function draw field, which require the function fl, but I transform it to have the right format, because to call the draw field I need to give x1, x2, and it will return me a function under the form of a list. That's why here I define this function just to have the right format. And here is a step. So I can see that I switch to Python. This is my function, I call it, and I can see here the vector field which corresponds to the linear vector field, but in draw field it has been normalized, so we can see that all the arrows have exactly the same size. So now what I can do also, if I will try to draw the original function, so I will call it f, and it will correspond to, I will lambdify the function f, capital F, so that this expression will be transformed into a function. I will not have to write another function. Again, this one I will define the function f underscore from this one, which takes the two arguments, and from this I will be able to draw the function, this function. I draw it, and I can see the function f. So it's better to have a better view. I will superpose these two pictures. So I will here draw like this, and I run this function, and I can see the superposition. Around x bar, the two functions are exactly the same, but when I'm far, there is some differences. It is normal. One is a tangent of the other one. So this field corresponds to a representation of my function f. So it means in this frame x1, x2, if I take a given x, such as this one, this arrow represents f of x. Here, f of x equal to 0. The trajectory are like this. If I take a point, they will turn like this, performing something like this, which is not an ellipse, not a circle, because the system is nonlinear. Now, if I look at the tangent system, so the tangent system was f of x equal minus x2 plus 1 x1 minus 1. So this tangent system is similar, especially around x bar. And here I have x1, x2. Now the linear system associated to this, I will draw it green, so it's called x tilde dot and corresponds to a matrix 0, minus 1, 1, 0, x tilde. So it's this one, except that the 1 has been removed. Then it corresponds to this system, but here I have x tilde 1, x tilde 2. If I apply this dynamic for the same initial condition as this one, in the affine system, the tangent system, take the same. I will obtain here something which is an ellipse or a circle. Exactly because this system is affine. And this system in the green, so in the variation frame, it will be correspond to a circle centered in 0. Last question is calculate the poles of the linearized system and discuss. So question number 3. The matrix A corresponds to this, and I have to compute the characteristic polynomial to find the eigenvalues. So I will compute the determinant of S identity minus A, which corresponds to the determinant of S minus 0, S minus 0, and here plus 1, and here minus 1. If I compute this determinant, it's this. So there is two eigenvalues, lambda 1 equal I, lambda 2 equal minus I. In the complex plane, there are here and here. Recall that on the left part it is stable, on the right part the eigenvalues corresponds to poles that are unstable, and here they are at the limit, and moreover they are not on the real axis. So it corresponds to trajectory that oscillate with respect to time. So if I integrate the linear system, I will obtain something like function like this. It corresponds here to x1 tilde or x2 tilde, and here it will have the form alpha multiplied by sine of t omega, because here it's 1, the distance. So here omega equal 1 times t plus a shift in the phase. Okay, so this oscillation corresponds to oscillating trajectory, and in the state space, the green one, I will obtain a disk like this, and the projection of this disk like this to a projection like this with respect to time t. So t here, I will obtain something, a projection here t is like this, and the projection will do, if I turn around a circle like this, then if I start here, I will obtain something like this, where here I have t, and here in my picture, since it is a projection, it will correspond to x1. So about the interpretation, I have an oscillating system because the eigenvalues are pure imaginary.